So velocity is a vector quantity, which means it has a direction. You move in a particular direction. Mass is scalar because you just have a mass. It's not in a direction. So momentum, when you multiply these, the momentum has a direction. It's like velocity, only it gets multiplied by the mass. So if you're moving in the exact same way, let's say on a bike, if you're moving at the same speed and in the same direction as a car, then you would have the same velocities, but you'd have different momenta because in order to get the quantity of motion, it's not just your velocity. You have to scale that up. You have to multiply that by how much mass happens to be moving. And you can kind of think of it like here's an object, here's it moving with an arrow representing the velocity. I gotta do so many things. That's a big one. Like that, this has a particular velocity, but if you had more matter, I don't know, 5 of them, with the same velocity, they're all moving together, they're gonna hit a little harder than if you just had one thing. Oops. They may be moving at the same speed, but they have different amounts of momentum. Like for instance, well, anyway, I think that's straightforward. So this is how you come up with what's called the quantity of motion. That's what Newton would have called it. But it is what we would call the momentum of an object. It has a direction. It includes the mass. The units for this thing would be kilograms for the mass times meters per second. So we'll say kilogram meters per second. That's a unit of momentum. Now, the thing that people were trying to resolve, so, the physicists at the time were able to figure out, okay, if we know how something's moving, we understand how it's accelerating, we can predict where it will go and where it came from. Then if we theorize about forces and the way forces work, and we now can mathematically combine forces and then use Newton's second law to translate that into the kinematic equations. And now we can kind of explain why things are moving, and we can similarly predict how they will move. The issue was collisions, that when things would collide with each other, it would sort of wreck the motion that was going on before. Two things might have been moving in a particular way, easily predictable. And then they touch very briefly. And after that, they can be moving in very different ways that your previous prediction didn't match. Like you can predict them so long as they don't bump into anything, where they will go. But once they do bump into anything, how do you account for that? How do you know how are they going to be moving after the collision? Now, that's where momentum started to come in. It was not alone. What people started to believe was, like when you had like if you think of playing pool, I have the cue ball and I hit the cue ball and it moves towards the racked other balls. When the cue ball hits the other balls, sometimes it stops and the other balls start moving. Probably none of them potentially move as quickly as the cue ball did when it struck them. People were starting to believe that there was something that the balls were passing back and forth, that there's this motive stuff that somehow moves from object to object during collisions, and that they sort of split up. And Newton, I believe, was going down this route and was coming up with this notion of momentum. And he would have referred to that as the quantity of motion. And this was an idea, which is an odd idea, but it ends up being one of the most important, the type of idea in all of science. This was the beginning of a sort of formulation of a conservation law. So what is momentum? Well, we can talk about that in a little bit. But it's why it's really important is because to some extent it's a conserved quantity. It's a quantity that is not created or destroyed normally in a lot of problems. It seems to be conserved. It seems to be the same before the collision and after the collision. And that was, again, this quantity. Take the mass, take the velocity, multiply them. There's something about that that's special, that helps us understand these collisions. There was a rival camp which believed in this living force. There's this living stuff inside of things, not momentum. They weren't referring to momentum, but they believed that there was this stuff, and they were religious. They believed that God instilled an amount of stuff in the universe, and that's all there is. Now things just pass this living force back and forth. What they were getting at was more related to mv squared rather than mass times velocity. When you square the vector, the directional thing, it loses its directional aspect, and it just becomes kind of like speed. It's just, or mass. It doesn't have a direction. It's just an amount of something. But they were looking at this quantity instead. And now today, if you take half that value, this is what we would refer to as the kinetic energy of an object. So, which is also extremely important concept, actually deeper than the momentum one. But we had those two rival camps that were both trying to understand collisions and how to predict what would happen in a collision. One camp was going with momentum, and one camp was going with energy. And they both turned out to be right in certain ways. They're different, but they both show up in helping us understand collisions. They're kind of similar in the way that people kind of invented them, but they are different. Let's see, how much do I want to say about energy? We'll be getting into energy after momentum. But energy is another usually conserved quantity. And that's an even kind of weirder one. Momentum you can kind of make intuitive sense of. Momentum is motion. It's how you're moving. If I change your momentum, I'm changing how you're moving. Energy was a little different. It's related to how you're moving, but it's not exactly your motion. both of these seemed interesting. Energy seemed more mysterious. But these are things that you can measure things about a car or a plane. There's these quantities you can measure, and if you multiply them in the right way, or square them, or divide by this, whatever, you can come up with a number, and that number will never change. That's what's interesting about it. What is that number represent? Like what is that in the world? What is energy? No one really knows. It's a quantity. It's a amount of something. It has units. They're odd units. Like if I looked at this formula for kinetic energy, it would be kilograms times meters squared divided by seconds squared. A little different than the momentum unit. These units we give a different name, kind of like the Newton. We gave the Newton was the force, which was kilogram meters per second squared, per second. That was a Newton. I'll write that. So this represented force, and we called that a Newton. This is going to represent momentum. I don't think it really has a name. And this one's representing energy. We call these joules, after the guy who came up with the idea. Well, I'll explain in a minute what he came up with, I guess. But these are, so this is a quantity that if you use this formula and you calculate it for things, for the most part, that quantity will stay the same at all time, that you'll always have that. It never goes away, which is interesting and mysterious. Like, what is it? It's kind of weird. But anyway, you have those two notions, and these are both quantities which are in some circumstances conserved. So about that conservation. Momentum on its own was not completely capable of telling you if I have two objects and they collide into each other, what are they going to do after that? Well, with momentum, you had the before picture, and you can't just come up with the after picture of how they'll be moving. I'll just put little lines on these. I don't know. And then they're flying away from each other. So here's before. I'll just do that. And then you have after. You kind of have to know what one of them is doing after. Then you can figure out what the other one's doing. So this object over here, you can calculate its momentum. Take its mass 1 times velocity 1, and then you can find its momentum, mass 2 times velocity 2. And those are the momenta for those two particles.